All right, so yesterday we talked a bit about projectile motion, okay, kind of just the basic principles of it before we went into horizontally projected projectiles. Okay, so quick review. A projectile is any object that's in motion in the Earth's gravitational field. That would be the motion, I mean unpowered flight. Okay, a plane or a rocket are not projectiles because they have an external source of power and force exerted on them that can help them to defy gravity. Okay, unpowered flight means it's flying through the air and it is going to follow an arc that eventually re-encounters the Earth, hopefully. Okay, so all projectiles then have a horizontal component to their motion that is a constant velocity type of motion, v equals d over t. And they all have a vertical component that undergoes accelerated motion due to gravity. Those two things happen concurrently, that is, at the same time. So, see what you remember from yesterday. We did 3 or 4 like this yesterday. Okay, this is a horizontally projected projectile. Okay, ball rolls off a flat 1.2 meter high table and hits the floor 0.85 meters from the base. What speed did it roll off the table at? Okay, you may have an example like this one from yesterday if you get stuck. I forgot to record all of that. Okay, so what we end up with there, guys, we calculate the time using the vertical information, okay? Then we use the time from the vertical information to calculate the horizontal speed, which is the speed it rolls off at. Okay? All right, I guarantee you on your unit exam, you will see one projectile motion that's horizontal and one like the stuff we're going to look at today, which is projected at an angle. All right, so these are the ones that will involve having to do a little bit of vector stuff, and I do mean just a little bit. You guys know how to find x and y components. If I give you a diagonal line, that's the extent of the vector stuff that you have to do with an angled projectile. Okay, because if it's angled, it's moving horizontally and vertically at the same time, so you have to find its x and y components to get its initial vertical velocity and its constant horizontal velocity. Okay? Everybody with me there? All right. Now, we have a lot of videos today, but we'll intersperse it with doing problems related to them. All right. So the first one we're going to show you is this one that was actually kind of at the dawn of YouTube. You can imagine how long ago that was for you. Okay. Not that long when you're old like me, but it was one of the first kind of viral videos that was on YouTube. And it's these guys built this big, giant slip and slide. Okay, and they had a ramp at the end of it. And so the guy would slide down this really long hill and then fly off the slip and slide through the air, a seemingly insurmountable distance, and land in a little inflatable pool and somehow survive. Okay, so, okay, now when this first came out, I mean, you have to remember that you couldn't watch a lot of things in HD, you know, your internet speed was a lot slower then. This looked real enough. I mean, if you have any background physics knowledge, you take one look at that and you go, I used to have one of those inflatable pools in my backyard. Okay? There isn't that much water in there. Okay? If you jumped into that pool from right beside it, you could hurt yourself by hitting the bottom. You would fall all the way to the bottom that quickly. There's no way that somebody who flies through the air as far as that doesn't destroy that pool, because you had to be careful getting in and out of it. If you pushed down on the rubber rim of it, it would collapse and all the water would come out. Okay? There's no way you land in that thing without completely destroying the pool, or at least moving the wooden deck that it was sitting on a little bit. And also, oh yeah, breaking your back, okay, when you landed in it. Okay, I mean, there should have been, but you should have hit that thing, hit the far edge of it, had it flip over, dump all the water out, and then there would have been a need for an ambulance or a coroner, okay, one or the other, because that would not have ended well, okay, for that person. But it looks real enough, okay? So real, in fact, that this was one of Mythbusters' biggest myths. okay, when they were big and on TV. Okay, they actually did the whole thing. They built the whole slide and tried to replicate how far the guy went. I'll show you that in a little while. Okay, but it was actually, I mean, it shows that they have the greatest job in the world. I mean, you get to make this big slide and slide down and fly off into a lake, like, and get paid for it. Career goals. It's too late for me, but maybe for you guys. All right, so let's have a look at this. Oh, that's the wrong one. That's the generally, I haven't shown you that one yet. Oh, I passed it maybe. Here it is. Okay, so this is our setup, okay, for it's called the mega whoosh. Okay, so they go down the big hill here, and they go up the ramp, and they fly off the ramp. We'll say the ramp's angled at 30 degrees. And they fly off the ramp at 20 meters per second at a 30-degree angle above the horizontal. And then, of course, they fly through the air along a projectile arc that encounters the pool. Okay? That part of the video's not bad. Okay? The person does follow a projectile arc, okay? And the pool is actually level with the end of the ramp. They go up, obviously, through the air and then come back down to the pool, but they don't actually have a change in height, vertically speaking. Okay? The end of the ramp and the pool are actually level because that pool is up on a hill, okay, a little ways away. So here's what we know. We know they shot off at 20 meters per second. That means they're moving horizontally and vertically. This triangle that I've drawn here represents time 0. Okay, so the instant they leave the ramp. Okay, so if I find the x component of that 20 meters per second at the 30-degree angle, that'll be the rate at which they move horizontally the entire time that they're in the air. Agreed? Because that part's not going to, I mean, we're going to negate air resistance and say that there was no air resistance, they just flew through the air. Everyone all right with that part? Okay. The y component is also a velocity, because the hypotenuse was a velocity in meters per second. But we know vertically that gravity is going to change their velocity immediately. So when I calculate the y component of this, I have to keep in mind that I'm only calculating the value of y at the instant the projectile starts. Okay, that is, the person leaves the ramp. So that would be their initial vertical velocity. Everyone with me so far? All angled projectiles have this thing fundamentally in common. Okay? Okay, so here's what I want to do. I still want to treat this like any other projectile motion problem. I want to break it up into the vertical parts and the horizontal parts. What do those two things have in common? Only one variable that they have in common, time. Okay? You're going to be traveling horizontally and vertically until you hit the pool. Right? And then time ends for you because you die. Okay? And the motion ends as well because you hit the pool. All right? So I can now put in a few things. Vertically, I know this. I made it negative here. Why? I didn't make it negative before. Right. In this one, we change direction in the vertical dimension. This thing starts up and finishes down. All right, so I'm going to make down negative. All right. Right now at time 0, that's about all I know. That's it. Okay. So now I got to start calculating a few things. V horizontal is the x component of my projected velocity. Okay, the hypotenuse here, that's the projected velocity. A question would call that it flies off the ramp, or it's launched at, and it'll give you a velocity. And it'll say this many degrees above the horizontal. That's your projected velocity. You never use that to calculate anything except x and y. Okay, it's never part of anything else. All right, so that's going to mean that this is V horizontal. Okay, so I'm going to go cos of 30 degrees times 20 meters per second. That number will be the rate at which the person flies through the air horizontally. Right, cos of 30, okay, times 20. All right, so this person, while they're flying through the air, is covering 17.3 meters every second horizontally. Okay? So if I was watching their shadow along the ground, their shadow would be moving at 17.3 meters per second along the ground. Okay? Pretty fast. Faster than you could run. That's like Usain Bolt fast. Okay? Super fast. All right. The y component is going to be their initial vertical velocity. So how fast are they moving upwards vertically at the moment they leave the ramp? That'll be the sine of 30 times 20, which is 10. And it's up. Okay? So the instant they leave the ramp, they're moving upwards at 10 meters per second. That's fast. Okay. I don't feel like I have that much information here. There's one other piece of information. You're never told this, but it's something we have to understand is true. If I throw this marker straight up in the air and catch it at the same height I threw it from, so it just comes back down to my hand. If I threw it up at 10 meters per second, how fast was it going when it came back to my hand?
Meters per second.
Exactly. Exactly the same speed in the opposite direction. Think about it this way. When it leaves my hand, the second I'm not pushing on it anymore, it's already being slowed down by gravity. Okay? So it's going to slow down, slow down, slow down at 9.81 meters per second squared. It's going to get to its maximum height, where for an instant it will what?
Stop.
Right. And then it will fall exactly the same distance back down to my hand at exactly the same rate of acceleration. It had better get back to the same speed it left at. Those two things are identical, yet opposite. Okay? The time, the distance, the acceleration, they're all the same for both parts of that flight. So it had better get back to my hand. What goes up must come down. And it must do so at the same speed it left at, because everything else is the same. Okay? This is part of why the myth exists about don't shoot a gun straight up in the air. Because in the perfect physical world, the bullet will come straight back down to you at exactly the same speed it left the gun at. That's only in the perfect physical world. In the real world, it doesn't happen. Okay? Not that shooting a gun off for any reason is safe, but okay, once the bullet gets to its maximum height, it'll actually tumble on the way back down, which reduces its terminal velocity. We don't deal with the real physical world when we do projectile motion. It makes it a little more difficult. We imagine there's no air resistance of any kind and everything's perfect. Okay? That's actually more dangerous in that situation, because that means the bullet would be going exactly the same speed it was fired at when it comes back down. That's certainly dangerous. Okay? Everyone follow me on that? That's why starters pistols use blanks and not bullets. Because we wouldn't want them coming back down onto the javelin area or something like that. Okay? It's also why you're not allowed to discharge firearms in city limits. If you have that angled at anything other than straight up, it'll follow a projectile arc and could very well be deadly when it comes back down to the ground. Okay? All right, so there's our other piece of information then. If I know that it left at 10, that means it has to come back at 10 in the opposite direction. Now, that is only true if the overall displacement vertically is 0. If it falls further, if its impact point is below, then it's not true anymore. Okay? Everyone all right with that? Okay. Vertically speaking, I have acceleration, VI, and VF. What can I calculate if I have those three things? Time. Can I use time on both sides? Okay, that's useful. So A equals VF minus VI over T. Okay, so if I manipulate this, I can get the time. So VF minus VI over A. So So that's negative 10 minus 10 divided by negative 9.81. All right, so negative 10 minus 10 divided by negative 9.81. So this guy's flying through the air for just over 2 seconds. It seems about right, right? Through the video, he's flying through the air for 1/1000, 2/1000 before he hit the pool. Okay, 2.04 seconds. Okay, is this a calculation, if this video was real, that these people should have done?
Yes.
Because it'll allow them to figure out what?
How far could the
Exactly. Now that I know how long that person's in the air, and I know how fast they were traveling horizontally, I can figure how far they'll fly through the air, and I'll know where to put the pool. An important piece of information, I would think. Okay? This is how, like, if you went into, let's say, like the Army or the Marines or something like that, and you went into artillery. This is the kind of calculations you would be doing all the time to lob artillery shells at your enemy. Okay? You want to know how far away your enemy is, so you know how much powder to put in or how much to angle the barrel of the artillery piece so that the shell lands on the target. Okay? If you were like me, when you were in university and young and stupid, you might have done something like this with your engineering friends with a bungee cord water balloon slingshot. Okay? We had one really nice day right before exams, second semester, and we were on top of our dorm and we could see into quad from there, and we thought, maybe our minds were a little skewed at the time. Perhaps we had been imbibing a little before this, and we thought, hey, we should totally lob water balloons over the Student Union building into quad and hit people with them. I know, you're looking at me going, Coda, that's a terrible idea. I totally agree with you. It was a terrible idea. Campus security also didn't think it was a very good idea when they showed up. We probably wouldn't have gotten in too much trouble, except we also decided that they looked like they were really hot and that we should hit their vehicle with the water balloon. Yeah. Campus security jail is probably not like real jail, just saying, okay? But yeah. So, this is the kind of calculation you would do. Now, my buddies were engineers, so they could do these kinds of calculations virtually in their head, and we were deadly accurate, okay? We just had a buddy giving us ranges, okay, like on a walkie-talkie, because cell phones were things that looked like a car battery then, okay? So he was just telling us, yeah, so-and-so's, this many meters away, and firing away, okay? Yeah, it was like, yeah, it was a scene, man. It was a scene. Okay, so now that I know this time and this speed, I just have to do a V equals D over T calculation to figure out where's that pool got to go. Okay, so D equals V times T. So we take our 17.3 and we multiply that by the time. All right, I better put that pool 35.3 meters away if I want to live and land in the pool. I don't think that would cause you to live. I think you'd die anyway, but anyway, that's the way that video works. All right.
How deep does the pool have to be to survive?
I think you would need several meters of water for that to be. And you also have to remember, you're coming in like this, right? So you've got some horizontal travel.
Yeah.
When he hit that pool, he should have literally flipped the whole pool over, right? Because of his horizontal component. When he hit, like, the water went almost straight up, a little bit gushed over the side, but that was it. That was not the splash that impact would have made, okay, in there. All right, I'm going to show you how Mythbusters busted. That's how all projectiles work, right? You should be able to continue to lob the same thing and hit the same spot each and every time, okay? So that part of it, fairly believable. The distance, no. They actually found out later that it was done by CG. So it wasn't a real thing, they had faked the whole thing, okay? And it wasn't real. Okay, now we did that one. Here's the one I was looking for. Okay, well, we'll do this one here. Okay, I don't know if anyone ever saw this show. It's not on TV anymore because, well, there was a Confederate flag painted on the top of the car. It's not really a very culturally sensitive icon to have on the top of a car. The show itself was actually, there wasn't really any, other than that, anything really wrong with the show. But the Dukes of Hazzard was a show from way back in like the late 70s, early 80s, where they would, this family of moonshiners was always on the run from the law, whatever. And apparently the county in which they lived had no bridges over anything. So they always had to jump their car over every creek and lake and whatever because there were no bridges. And they always did it, and they always never wrecked the car, which was ridiculous, okay? Because actually through the course of the show, they destroyed several hundred beautiful 69 Chargers, okay, in this show. In fact, by the end of the show, they were trying to straighten the frames and jump them more than once. They were using other Dodge products like Challengers and photographing them from different angles where they would look similar because of their bodywork. By the end, they had basically run out of jumped cars because every time you jumped one, that was the end of it, it died. Okay? You can actually see, if you watch the show, sometimes when they reused a jump car because it's like going into the jump, but it's already wrecked. Okay, Anyway, I'm going to show you one jump in particular, okay, and then we're going to do a little calculation. This is the first jump in the series, okay, that they ever did. All right, so in this clip, it jumps over the riverbed, and the following information is known. Speed of the generally is 32 meters per second. That's roughly 120 kilometers an hour. Okay, it leaves the ramp. When it leaves the ramp is angled at 20 degrees. What's the distance across the riverbed, and what's the maximum height that the generally achieves in its flight? Okay, so what we have is this information is known. The projected or launch velocity of the generally is 32 meters per second, 20 degrees above the horizontal. Like all projectiles, it follows an arc that re-encounters the ground at the same height it was launched from. That's important, because that means VI and VF are the same number. Okay, so we know this side here, the Y component, is the initial vertical velocity. We know the X component is the horizontal component of that velocity. Okay, what we want to do is break this up into vertical and horizontal parts. Okay, let's see what you can do with this. You got to do X and Y components. Okay, what we're looking for is the horizontal displacement of the generally from its launch point to impact. Okay, give you a few minutes to try it on your own, and then we'll go through it together. Okay, so in any projectile motion question, if you're given this setup where you have the launch or projected velocity, the first thing you want to do is find the two X and Y components. Okay, so that helps us get VI. VI is going to be the sine of 20 degrees times 32 meters per second. So this will give us our upward directed initial velocity. All right, so sine of 20 times 32 meters per second, 10.94, and that'll be positive. 10.94 meters per second. I'm going to keep all the decimals in my calculator at this point. Okay, so that's VI. Since I know that it lands at the same height it's launched from, you assume that unless you're told otherwise. I know that VF is negative 10.94 meters per second, and I know the acceleration is negative 9.81 meters per second squared. All right, I'm trying to find this. I can calculate the horizontal component right now because I know it's the X component of the launch velocity. Okay, so that'll be the cos of 20 degrees times 32. Okay, so 30.07 meters per second. All right, if I'm going to get the horizontal displacement, I need to know what?
How long?
How long this thing is flying for. Okay, so I can calculate that with my vertical information because I have VI, VF, and A. So I go back and I use our good old Science 10 formula. okay, of A equals VF minus VI over T. I just manipulate for T. Okay, so T will be negative 10.94, my final velocity, minus 10.94, initial velocity, divided by my acceleration, negative 9.81. All right, so if I go negative 10.94 minus 10.94, that'll be the top. Okay, and I divide that by negative 9.81. All right, the general leaves flying through the air for 2.23 seconds. That's quite a long time. That's a good yee-haw, because that's what they would always say whenever they would jump. Okay, so they are going to fly through the air and scream yee-haw for 2.23 seconds. That time can come here. It's the one thing both the horizontal and vertical parts share. Okay. Now I know D equals V times T, and I have the two numbers. So 30.07 times 2.23 seconds. Okay. It is 67 meters across the riverbed. To give you a perspective, that is from that end of the track by the shed to just past where the path goes across the track over here. Okay? 67 meters. It's a long way to fly through the air in a car. Okay? Probably not going to end well, would be my first thought. Okay? It certainly didn't end well for the car, which was destroyed. But they were smart. They made it land in a cloud of dust so you couldn't see its destruction, and then it's more believable when the hero car drives away. All right, that's the first part of this question. It wants to know how far across the riverbed. But the second part of this question is, what's the maximum height above the riverbed of the general E? That we haven't done yet. So the maximum height is going to occur right here, halfway through the jump. Okay? From a vertical perspective, if all you could see was the vertical part of this, it would be like you were standing right where the car was going to land. Okay? And all you would see from that perspective is the car go up and down, because you wouldn't be able to see it from the side. Okay? Because that's all it does from a vertical perspective, is goes up to its maximum height and then falls back down. How fast is it going vertically at its maximum height?
30 meters per second.
Vertically.
Oh, vertical.
Remember when I threw the marker up in the air?
Stop.
Right. It stops for an instant. Okay? Vertically speaking. Obviously, the car is still moving. It's still moving horizontally. But from a vertical perspective, all this car is doing is being thrown up in the air and then falling back to the ground. So at its maximum height, its vertical velocity is 0 meters per second. And since this happens halfway through the jump, it would happen at what time? Half of this? Okay, so there's two new pieces of information, right? I'm trying to find the vertical displacement, how high above its launch point is it, when this is true. Okay, so when I'm trying to calculate the maximum height, I still have this number. This number is still true. Vertically, initially, it was moving at 10.94 meters per second, upwards. At the maximum height, VF is 0. And the time is half of 2.23 seconds. And the acceleration is negative 9.81 meters per second squared. Okay, so I could put in here, so half of 2.23 would be 1.15,
1.115.
yeah. Yeah, okay, so seconds. Do I have enough information there to calculate D? In fact, I have so much information there that there's more than one way to do it. Okay, I could use this formula or this one. I have enough information to use either one. I use the top one. Here's why. I find when people use the bottom one, they forget to divide the time by 2. And then they get the wrong answer. Because they forget that that maximum height happens halfway through the flight. Okay? I avoid forgetting that by using the formula that doesn't have time in it. Okay? All I have to remember is that at the maximum height, its VF is 0. Okay? Whichever one works for you is going to come up with the right answer. Okay? So I'm going to use the top one here, and I'm going to solve for d. Okay? So I'm going to bring VI over to the other side. So I'll have VF squared minus VI squared over 2a equals d. Okay? Plug in my numbers. 0 squared minus 10.94 squared divided by 2 times negative 9.81. All right, so 0 minus 10.94 squared, okay, divided by 2 times negative 9.81. All right. So the maximum height above the riverbed is 6 meters, 6.1 meters. Okay, that is well, roughly twice the height of a regulation basketball net. Okay, so imagine being dropped from almost the top of the gym. That's what happened to this car. Okay. Not too many cars are going to do very well if they're dropped from that kind of a height. Okay. All right, so 6.1 meters. That's the one way. Now I also said this formula would get me the same answer. All right, so I just want to prove that to you. I'm going to take that 2.23 seconds, and I'm going to divide it by 2, so I've got exactly half the time. Okay, and then I'm going to use that formula. All right, so I'm going to use the 10.94, because that's my VI. Okay, and I'm going to multiply it by the time. Okay, and then I'm going to add to that 0.5 times negative 9.81, okay, times the time squared. Oh, gee, I got exactly the same answer. Go figure. Okay. Those are the things I would ask you to do on a test. Okay? I would ask you to calculate how far it's going to travel horizontally and what would its maximum height. Okay. All right. That makes sense, everybody? It's a bit of work, right? But once you get the hang of how to do projectile motion problems, what it really comes down to is finding x and y, doing an acceleration calculation, and doing a v equals d over t calculation, and maybe doing an extra acceleration if you're asked to find the maximum height. Okay? All of these individual steps you already know how to do. All right. What do we got here for time? Okay. Let's look at an example of really bad movie physics.